Now that we are recording, I'll make that statement again. Today's focus is to help you identify the problem solving steps and the thought processes you need to go through for every force problem. And that starts with the question, is the object moving? You're generally going to have to read the problem and look at the diagram. Both of these things together are there for you for a reason. So you've got a water skier and you're going to look for information about motion here. If you don't see additional information about how he's moving, you assume he's moving at a constant rate. So we're going to assume simplicity until otherwise stated. All right. So when I get into this, I'm going to be using two different colors for my component parts. I've got this throw up green here and this nice lilac purple. Every other color is a bit too bright. And I guess I could technically pick one of these to be a nice dark blue color. So we're gonna replace that. Now we're gonna save it. All right, so it won't be throw up green anymore. There we go. And let me. Oh no, I replaced black. Let's replace this one with black. And I'll agree that the color palette's probably what I know about Cami the least. So you always want to draw in a axial plane or an axial plane. This is going to give you reference to direction, and it's how you determine if the forces are balanced. So if he's not moving with an accelerated rate, nothing says slowing down or speeding up, you're going to assume constant velocity. What does constant velocity mean about acceleration? There is no acceleration, which means one of two things. There's no forces acting in that direction, which is usually not the case, or the forces acting in that direction are balanced, which is that Newton's third law idea of equal and opposite forces. So I generally like to start down, then up, then I'll look left and right depending on what's acting. So let's start going down. What's acting downward on this skier? Gravity. So we've got gravity acting straight down. So I want you to notice the way I've chosen to draw my axis here. I've got it traditionally oriented with the X horizontal and the Y vertical. I don't think so. Nope. Fix that though. Yeah, I didn't. So gravity force going straight down. Is he sinking into the water? I'm assuming this is a guy. My bad. Are they sinking into the water? No. So that means there's a resisting force here. And now technically the resisting force here is a little bit special. If you look at the position he's sitting at, it's at an angle. We talked about this yesterday that skiers dig their heels in. That's going to put a normal force or a buoyancy force, you can call it either. That depends on whether you consider the skis part of him. If he's part of the skis are part of him, it's buoyancy. And if he's on the skis, then it's normal force. Doesn't matter what you label it, but it's up into an angle. So you're going to have that up into an angle. And I'm going to call this normal force. We're looking at just the skier. He's on the skis. So we got normal force there. And then what else do we have acting on him? Tension. All right. So right now we've got three forces. Does it seem that they are balanced? What else would you think would be acting on the skier and his skis as he's pulled through the water? There'd be friction, right? Because if you move along a surface, even if it's a fluid surface like water, you're going to have resistance. And so fluid friction, we call that what? The force of drag. So we're going to have a drag force this way. So I want you to notice that part of normal force is backward. That's why drag force is not super big here, because the normal force itself is kind of resisting as it runs into the bottom of those skis. So I told you I'm going to show you the component parts of every angled force. So we've got some X component where that is going left there. And then we're going to have some Y component where we're going to see the upward component. So in this case, only the upward component of force, normal force, is balanced with gravity. Or I could say the other way around, Gravity is only balanced by the upward component of normal force. All right, so the nomenclature for the components is the technical title for that force, and then you just give the direction. So you'd give another subscript of x for x, and another subscript of y for y. So that's going to be our first example there. Now in this next one, we've got a horizontal surface. You have kids in the sled as our system here that we're paying attention to, and the sled is being pulled up at an angle. So let's draw in our axial plane. We've got a relatively horizontal surface, so we're not going to tilt it. So is the cart moving, or is the sled moving? It's at a constant rate. So it is moving, but it's not moving at an accelerated rate. There's nothing that says speeding up or slowing down here. So we're going to assume based on constant rate, it means what about acceleration? That there is none, and that means that the forces in this case are balanced. So what's pulling down? Gravity. All right, are they sinking into the ground? Why not? What's resisting that? You got a normal force. All righty, so we have a normal force and a gravity force. All right, what's causing them to move sideways though? The tensional force up and to the right. All right, but they're moving at a constant rate. So what does that mean about this force here that's in the rightward direction? So we've got some component of x right here. What's resisting that? We're going to have a frictional force to resist that. So we're going to have a frictional force equal and opposite in the negative x direction here. So once again, we've got a y component of tension and an x component of tension. You would write those as the tension in the y direction and the tension in the x direction. These components matter when we're trying to determine whether forces are balanced, because the forces balance only in one direction. You can't say the total amount of forces all up and down, because think about it. Does gravity act on you sideways? No, it doesn't. It only acts vertically. So that direction is independent of sideways motion. We'll come back to that when we get to projectile motion. So we've got a dancer leaning on a table here. The table, is it moving? No, it's on a level surface, so we won't tilt our plane. So why is the table sitting on the floor? What's pulling it down? We've got gravity. All right, why is it not sinking into the ground? All right, so we've got the normal force up and out. Nice straight line there. Now, what has the dancer got to do with it? What are they doing? They're leaning, and in what direction? Let's follow that line of force there. It's going down and to the left. So you could call this a couple things. You could call this the applied force. This is technically going to be felt by the table as a normal force because it's contact. But I'm going to call it, just for simplicity's sake, the force of weight. All right, force of weight, the weight of that dancer. So we're going to have the force of the weight down and to the left. If we look, that means we have component pieces. We've got an x directional piece here and a y directional piece. So if we have the table stationary, what does that mean about the forces in the x and y direction? They must be balanced or equal. So what am I going to have to keep this table from sliding to the left? What stops objects from moving? Friction. All right, and you got to think, tables are usually pretty heavy. That's for a reason. It's so that you can lean against them, put stuff on them, bump into them without them just flying across the room. You wouldn't want your tables constantly moving if you leaned on it and it started moving with you. That's why we don't use TV dinner trays for everything. It'd be annoying. All righty, so those component pieces are what tells you there must be friction. If you didn't know that, you might not think, well, there's friction stopping it. So it helps you identify all the forces acting. So I wanted to go back before we get too much further and just show you how you're supposed to be signifying that these are equal. Something I've missed so far. When you do that, you're going to use congruency marks here. This is, again, that geometry skill where you're saying that this line is equal to that line. Technically, this line here is equal to that line there. I came up here and did this for these, I can't say that normal force and gravity are equal because there's an additional tensional force. So we've kind of talked about this before, but you lift up on things to make them easier to move sideways. It's because you're decreasing the normal force. And we'll learn later that friction comes from normal force because friction's a contact force and normal force is the force that results from contact. So you can't say that either of these upward forces is congruent with that. So I'm just going to have congruency marks here. If I added these together, then I could say they're congruent. So if I added in another vector and called it Fm plus Ft in the y direction, we'd be good to go. All right. So here we're going to see that the y component there is congruent with gravity. And technically the x component of normal force and the force of drag would add up to equal tension. So we can't say that that's congruent. I wanted to go back and clarify that so that you can see it as we move forward. So we're going to assume, I know that you see two slopes, and this threw some of y'all off for how you draw your axial plane, but he's in reference frame kind of level. He's in line with the y direction. So what's acting on him? Is he moving? No, he's stationary. So that means forces are balanced. So what's pulling him down? Gravity. What's keeping him from falling? Is he in contact with the floor below him? So can he have a normal force? No, he can't. So what's holding him up? Tension in both sides. And it's holding him in this direction and in that direction. And equally so. Neither one of these is bent at a different angle. So that means that tension in the rope here and tension in the rope here, we're going to call this FT1. You could call it FT to the right if you wanted to. You just need to denote which one is which. So let's look at this. We've got two angled forces this time. So we're going to have a y component force here. Y component force going up. We're going to have an x component force going left for this tension and right for that tension. So I want you to notice that the x components balance themselves out. So the rope is pulling him to the right as well as pulling him up. So if you were to add these two vertical components together, they would stack to a length. I'm just going to draw that in. I'm going to synthesize it just so you can see it. Oh, let me do that with blue since I'm already in that color. They would technically come together to make this line here, which would be the y components of these two tension, and that would end up, this would technically be congruent with gravity. All right. But that's not a real force. Those are component forces. So I can't technically say that. This is a hypothetical force that we're going for there. Yes. Yeah. That's a good point. So what am I doing with my axis here? I'm tilting it or rotating it because the surface is now angled. First time yet. So we've got a squirrel and it says that he's sitting still, which means stationary, and there is no acceleration on this squirrel. So that means that forces on the squirrel are balanced. So what's pulling him down into straight down? What's that? Gravity. All right, so gravity is going to be straight down. And here comes our first point that's gravity tilted. All right, now where does the so the squirrel's on contact with the roof. So what's the roof provide? All right, normal force. So you're gonna have a normal force coming out of the roof. All right, why is the squirrel not falling down? Because if we look, this gravity force here has an x component and a y component. Now this y component here is congruent with normal force, but what's balancing the x component of gravity? It's going to have to be friction up the hill. You got to think that friction resists motion opposite the direction of intended motion. So he would go down the hill if he could. So friction points up the hill parallel to the surface. And technically, this line here is congruent with friction. So they're equal. They're balanced. All right, we got Skier Joe over here heading down the hill. Now it says that you have negligible friction, which means that you can ignore it. It doesn't exist here in this example. So what are we going to assume he's going to do as he goes down the hill? He's going to accelerate. If you've ever skied, you already know the answer to that. If you've ever run down the hill, you also, like, if you try going downhill, you're generally going to accelerate pretty fast. The lack of friction here makes that even more so. All right, so what's pulling him down? Gravity's pulling him down and to the right. All right, so that gives us inherently an X component and a Y component. So we have two pieces here. So we've got part of gravity pulling him into the hill and part of gravity pulling him down the hill. The part of gravity pulling him into the hill makes the hill resist him and provide what? A normal force out of the hill. So right now he's being pulled down the hill, and these two are congruent. He's being pulled down the hill by FGX here. And there's nothing to resist him, so he's going to accelerate as he goes down. So in this case, we would say that net force is down the hill, and we could also say that acceleration is down the hill. All right, he's going to accelerate down the hill. On these next two, I'm going to, just looking at my time, I want to make sure we have enough. I told you about 25 minutes. Yes, Will. So he asked if there would be drag from air resistance here. You could draw it in, but it would essentially be negligible here. When we're talking air resistance, we're generally going to be looking at large objects in the air. You falling straight through the air, like full wide, like spread eagle, or with a parachute. So large surface areas. So if you look at him right here, one of the things that a skater does is they crouch their knees for two reasons: to become more stable and also decrease their size. So they're trying to decrease air resistance as much as possible. So in this case, we can ignore it. But if you did draw it in, you could draw it in as a small vector in here. You could call that force of drag here. But it would still be somewhat smaller than the downward pull of gravity. So he's going to accelerate down the hill. Good point. But in this case, we would generally ignore it because of his smaller size. So something like a squirrel, also you could ignore air resistance generally. But if you look at a flying squirrel, their bodies are built to kind of play off of air resistance. So it's kind of case by case, but good question. So while I've got the time, I'm going to go ahead and switch shares. So we're going to switch to a whiteboard for Zoom. And I want you to remember all of those examples had angles. They had component pieces and a hypotenuse. Yes, yes, you may. So I want you to remember that in every single one of those cases, the hypotenuse of what looked like a triangle. So I'm just going to draw one for example here. All right, so I'm going to put in an axial plane here. So if we're thinking about the kids on the sled, that's a good example. We had gravity down. We had a normal force up. We had tension up and to the right, and friction to the left. I think my stroke thickness, yep, that's what I thought. So we have a Y component and an X component. So Ft sub X and Ft sub Y. This right here is a triangle. You might not initially think about it, but anytime you angle a vector, you've created a triangle with reference to one of, technically both of our axes here. So if you draw a line in between two axes with reference to either axis, you've now got, or axis, you've now got a triangle. So I could technically show you that, I mean, you've essentially made a rectangle with the cross-cut, the diagonal length of the length of your vector. So I'm going to tell you that you're almost always going to refer to the bottom Y and one of the X's for your angle. So I want to remind you of a couple geometric principles. So if we have a box here, I feel like there's definitely a shape I could have drawn this in an actual box. Yeah, here we go. So if we've got a box here and you draw a, I guess, and you draw a line through it, you've now created two triangles. So in the case of a box, you've got a 45-degree angle, a 45-degree angle, and a 90-degree angle. The interior angles of a triangle must add up to 180 degrees. You are going to look at complementary angles for either side of this line and across these two where you have a right angle. So if you have 90 here, then that means that this angle, we'll say 1, and this angle, we'll call this 2, must add up to 90. And so by extension, this one and this one must also follow that rule. So if instead of a triangle, or excuse me, a perfect square, oh, I'm doing it in white this time, so let me undo that one. So instead of a square this time, if we're dealing with a rectangle, it gets a little different. Just wanted to make the clarification that here, we're still going to split it, but now we've got non-45-degree angles. You understand what I'm saying here? That this angle and this angle are the same. We could say that they are congruent. This angle and this angle are also the same. We could say that they're congruent. So you're getting some geometric proofs here, but the big idea is that congruency matters here because you're now creating these rectangles and you have to figure out which angle you're dealing with, because the angle is going to change what perspective you're looking at. So if you're looking at, for instance, this angle and this angle, we now know are not necessarily congruent if you don't have a 45, 45, 90 triangle, which is hardly ever the case here. So that means that picking the right angle really matters, or else you'll accidentally get the complementary angle and use the wrong trigonometric function. So let's bring in trig here. So if I'm trying to determine information about this, I generally have two ways of learning about leg lengths in a triangle. So just leg lengths, I've got the handy dandy, let's see if you can guess it, just based on what I'm doing right here. How would what would you call this approach? Using what? A, B, and C. The Pythagorean theorem. So that's the idea of a squared plus b squared is equal to c squared. So you could use this. That's a possibility. It's going to take longer because you're going to have to square things. You're going to have to remember what's A, what's B, what's C. If you can get the trig down, we will actually start using trig shorthand to represent these component pieces. So for instance, for the most part, we're not going to use the Pythagorean theorem, or you won't see me use it. You're going to see me use trig. So let me go ahead and show you what that trig looks like. I'm going to wipe this slate clean really quickly and then show you another triangle and identify some things about it for trig. We will, because I told you we're referring it back to the axis, right? We're referring it to the X or the Y axis. We're going to have a right triangle. So trig rules will apply here all the time. Traditionally, we're going to be looking, so if I draw in that axis, we're going to be referring back to the X axis or to the negative Y axis if you've got a tilted plane. So this angle right here, if you remember, we call it an unknown angle or an angle of interest, theta. And we have a couple things that we're going to talk about for theta. So theta has two legs that touch it. We've got this one that's at a diagonal, and what do we call that? This one's called a hypotenuse. I'm going to shorthand that for HYP. It's hip. So we've got this other leg length, and we call this the adjacent leg length because it touches it, and adjacent means close or touching. So I'm going to call that ADJ. Then this leg length is completely across from the angle, so it's called the opposite, and I'm going to call that OPP. So these are my shorthands. So when I write out the trig definitions that we're going to cover, I'm going to use this shorthand. So if I want to use trig, I have to remind you that these are what the leg lengths are called, and picking the angle changes the leg length. For instance, I told you we could technically make this a square or a rectangle. And now we will have a complementary angle that is not congruent. And this here would be, I'm going to do this in a different color. So if I draw this in as red, so this angle here has an opposite leg length that is congruent with the adjacent leg length of the other angle. And it's going to have an adjacent leg length here that is congruent with the opposite leg length of the original. And your trig functions would be backward. Do you understand why I'm saying this? That's why angle picking is really important, or determining the correct angle is important. And I'll help you remember that in just a few. So how do we use sine, cosine, and tangent to do this? Do you guys remember the... So we've got a mnemonic device that you were all given and asked to memorize. So it's 3 sets of letters, and this mnemonic device gives you the formula in words. And you have to remember some extra words that aren't really put here. So we got so, ka, toa. And this idea is here. I'm going to just draw these arrows now with this thickness of pen so that I can switch down. Sine of theta, that part's important, equal to OH. Opposite divided by, or over, is how most people would say it, hypotenuse. All right, this one here states that cosine of theta is equal to, and this is AH, adjacent over hypotenuse. And then here, this one states that tangent is of theta equal to, and this is OA, opposite over adjacent. These 3 statements are what you will use to determine the leg lengths that you don't know, given the information that the hypotenuse is almost always, like 95 to 96% of the time, going to be your hypotenuse. So in the example of tension that I gave you earlier, where we had a traditional axis, and I'm just going to draw on tension here. Tension was at an angle. The tension is now your hypotenuse. And you've got 2 leg lengths, one adjacent leg length, I'll call that A, and one opposite leg length, O, where your force itself is the hypotenuse. So on that note, I want to go ahead and make this statement while we're thinking about it. When you have a tilted axis, because you have a tilted surface, remember that gravity goes down at an angle? Gravity is always your hypotenuse, which means, and this is an important fact, that your angle will be from the y-axis. So it's, what is it tilted from? Traditionally, it goes directly parallel with the y-axis. So as you tilt the hill by theta degrees, you also then tilt gravity by that many degrees. Does that make sense? That's how much you've changed from horizontal, and gravity used to be perpendicular to horizontal. So it's going to change proportionally to the amount of tilt of that hill. That is a really important fact, because if you use the wrong angle, and this is the one people use the wrong angle for every time, you're going to use the wrong trig functions and you're going to solve for the wrong leg length. All your answers will then not be right. And the reason that matters is because sometimes you use these leg lengths and their congruencies to solve for another force. So for instance, if you've got gravity pulling down to the right and it's not moving, meaning that there's friction, don't you remember that the x component of gravity is proportional or congruent with friction? So if I asked you to solve for friction and only gave you gravity and the angle, and you accidentally solve for the y component of gravity instead of x because you used the wrong angle, then you'd end up with the wrong answer for force. So this distinction is important, even if it is kind of a stickler of a rule. Alrighty, so sine is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. So you're going to be using these ideas generally to solve for a leg length, not to solve for the sine of an angle. So that means you're going to have to use a little bit of algebra here to solve. And I've told you that usually the force is the hypotenuse. And lucky for you, that's the denominator. So you just multiply it over. And so traditionally, I'm going to erase this axis right here. If I can get all the little tiny moving pieces. Traditionally, when you're solving for the leg length, you're going to be solving for either the opposite or the adjacent leg length there. So that means that here, let me make that an O. The opposite leg length is going to be equal to the hypotenuse, and you multiply the hypotenuse over times the sine of theta. And consequently, or subsequently, the adjacent leg length is going to be equal to the hypotenuse multiplied by the cosine of the angle, theta. And then here, tangent is what you usually won't use tangent unless you don't have the hypotenuse and you've been given the components, which is very rare. Not going to say you won't see it or that it won't be useful, but you will probably try to avoid it if you can help it. But you would end up using trig if you wanted to solve for adjacent. You could, or if you wanted to solve for opposite, you could multiply that adjacent over. So these two statements are actually, so if we're looking, the opposite leg length is the force times sine of the angle. The adjacent leg length is the force times cosine of the angle. So let's do an example problem. Do you have any questions before I do that? It's pretty straightforward. So if we go back to that idea, I can do it with this tensional force since I already have it drawn. I'm going to say that the tension is 20 newtons, all right? And that you're pulling at an angle of, let's say, 30 degrees. All right, so theta is equal to 30 degrees. I know my hypotenuse here, the force, is equal to 20 newtons. And I want to find my opposite, or I already started writing A, so I'm just going to make that adjacent. Opposite. I want to find my component pieces. Because remember, in this example, we said that friction was congruent with the x component of tension. So I want to know what friction is, but I got to figure out what tension is first. Yes. Yes, you may. So we have 30 and 20. That's all you need to figure this out. So if I want to solve for the opposite leg length, so in this case, this would be opposite here is F T sub y equals opposite, and F T sub x equals adjacent. Do we see why? This is the x direction that's adjacent to the angle. This is the y direction opposite of the angle. So we know that adjacent is equal to, well, right here it says that adjacent is equal to the force, or the hypotenuse, times the cosine of the angle. So we've got 20 as our hypotenuse, so it's going to be 20 times cosine of our angle of 30 degrees. All right, so we'll do cosine 30. When you do this, the first thing you need to make sure before you plug this into your calculator is that you set your mode to degrees, not radians. So that is the mode button, which is second to the right, or second from the left. It's right next to the second button if you are using a TI-84. You're going to hit mode, and then you just need to make sure it's in degrees. And otherwise, you're going to get the wrong answer because it's going to be measuring in something that's traditionally used in calculus or trig. Really, radians is pretty common in trig as well. But for these, we're using degrees. So it's going to be 20 times the cosine of 30. This will give us a component piece of 17.3 newtons. Now, we're going to do the same thing to find the y component. The y component will be the opposite leg length, which will be the force, the hypotenuse, times the sine of the angle. So that's going to be 20 times the sine of 30. All right, so 20 times the sine of 30 is, anybody who knows the sine of 30 knows that this is 10. Sine of 30 is 1/2. So technically, because it's at a 30-degree angle, that means that the half of it is straight up and far over half of it is to the right. So most of tension here is to the right. And I'm going to show you why before we leave. But in this case, what I was looking for was this right here, the x component, because that's, so then because of this statement, I can then say that F of friction is equal to the x component of tension, and then I can say that it is equal to negative 17.3 because it's in a negative direction, it's to the left. So this right here is what we will be doing for the rest of class. Now, I've gone ahead and made it quantitative. Tomorrow, we're going to be doing quantitative, just regular old trig practice. But for the first several days of actual worksheets for physics, you're going to be qualitatively saying, are they balanced? I wanted to go ahead and prepare you for what comes next, which is saying, okay, so if they're balanced, calculate one in order to calculate the other in that direction. So I told you I would show you why the 30-degree angle has half of it pointed up and then more than half of it pointed right. This is a concept you already know, but it's one worth mentioning. And I'm going to do it in this left corner here. So if I've got an axis here and I draw a vector, so what I'm going to do, I'm going to draw a line. Let's see what their vector looks like. That's actually perfect. So I'm going to draw this vector at this angle in that color. Hopefully I can copy this. We're just going to, and I draw that same vector at the same length at a different lower angle. And I draw that same vector oh no, at a different angle. That's about the same. So the vectors are the same length, but I want you to notice what happens. If I draw a dotted line connecting it, an angle below 45 degrees is much larger here. X is greater than Y. Because you're below 45, you've gone farther to the right than you went up because you're below halfway of that angle. At 45, here, sorry, my mouse moved right in my hand. You get the point, though. That's supposed to be a straight vertical line. In this case, Y is, we'll say, approximately equivalent to X. They're almost exactly the same. If it's a perfectly 45-degree angle, they are equal to each other. And if we have a very vertical line here, notice that the line itself is the same length. The hypotenuse is the same. In this case, Y is greater than X because you're above the 45-degree line. So that just qualitatively tells you that you should expect an angle greater than 45 to have a Y or a vector angled at greater than 45 degrees should have a Y component larger than an X component. An angled force at 45 degrees should have an X component equal to its Y component, because the cosine of 45 and the sine of 45 are both the same number. All right. And then if you have an angled force that's angled at an angle less than 45 degrees, such as 30 here, which we just showed, then you're going to see that the x component is greater than y. So this right here is the explanation for why the x component of this tension was greater than the y component of it. It's the angle it was oriented, which is why angles of forces matter. If you want to take off the weight, if you wanted to angle it upward, you'd want to make sure that the angle you applied the tension was above 45 degrees. If you want to pull it sideways more than you want to pull it up, then you want to make sure that the angle that you apply your force at is below 45 degrees. So when we're talking about leverage later on down the road and how you get something to do something as efficiently as possible, the angle of the force is, if you've got the same force, the only thing you can really control. And as you live life, you'll find that the angle you apply a force at really matters. Like exactly where you're holding something. If you're trying to balance it, if you've ever carried laundry in one hand, something I do. I have my laundry downstairs. If I carry it upstairs and my hand is off balance, it's not supporting the whole weight, there'll be an angled force. It'll fall out of my hand and I'm picking up laundry on the stairwell. All right. So your force's magnitude is as important as its angle. So we'll go ahead and stop there.